Alright, here we are with the very last example. What we just saw a moment ago was that the arctangent of x, recopying example 7, you can see it's really coming from up here at the top right part of the screen. That's x minus x cubed all over 3 plus x to the 5th over 5 minus x to the 7th over 7. This is really sigma n equals 0 to infinity of negative 1 to the n, x to the 2 to the n plus 1, all over 2n plus 1. And what we have very quickly is the following. We're trying to get x times arctangent of 2x. Here is something we are going to use repeatedly. We're going to do this so very often. We could rewrite this series as arctangent, just have a little blank space here. Everywhere where we have an x, we could leave that as a blank. And we're going to replace that with 2x. So just almost done with recopying here. We could do the same thing with sigma. And by the way, even when we get to the next section, we're going to continue to use this method of working with the power series that we've just developed or that we know and making some substitutions in it. So we're going to see arctangent of 2x. Well, everywhere where we see a little blank here, we're going to put in a 2x, and very quickly we have a new series representation for this new form. And we'll say minus, etc. Over here in sigma, we go from n equals 0 up to infinity, negative 1 to the n, 2x to the 2n plus 1. Now, by the way, what I really wanted to point out from up above is that this is going to be arctangent being true, converging for the absolute value of x less than 1. We're seeing that this is true just as well, but as we make this substitution, we now have 2x less than 1. And just cleaning this up a little bit, we're going to see that the arctangent of 2x will be 2x minus, well, this will become 2 to the 3rd, which is 8, 8x cubed all over 3, plus 32x to the 5th all over 5. Continuing on into sigma, we know that we do in fact have an alternating series, of course. We still have this negative 1 to the n, but this will become 2 to the 2n plus 1 x times the 2n plus 1. Again, these are odd numbers, 2n plus 1. And this is going to be, if we divide both sides by 2, the absolute value of x less than a half. Well, that's not quite what we'd like. What we need to find is x times arctangent of x, or arctangent of 2x. It looks like on the left side we just multiplied by an x. We're going to multiply every power in this series expansion by x as well. Every power of x increases by 1, including what we see in sigma. So we'll have negative 1 to the n, 2 to the 2n plus 1. This will now become x to the 2n plus 2, all over 2n plus 1. By the way, we're still going to have the absolute value of x less than 1/2. And you can see we really haven't had a substitution to affect that absolute value. It would only take a moment to see if this in fact is correct by checking the first term, well, checking the 0th term, n equals 0, then letting n equal 1 and working on from there. If you just took a moment to do that, you would see that that is in fact what we have. So very nicely we see that we can take a function that we have a power series for, make corresponding substitutions for x. If we need to multiply by x to a power out in front of that function, we'd multiply every term in the power series by that x to the power as well. Well, hope this is making sense. We're going to continue to work on this, and in section 12.10 we're actually going to talk about another way that we can actually derive or create a power series, especially if we are not able to work off of one of the ones that we have today. So best of luck to you, and good luck.